We're starting Unit 3. This is going to be a very busy session. We have a lot to cover. Let's take a look at what I plan to do with you in this session. We're going to look at angles other than the quadrant and our special angles. What were those? Well, the quadrant angles, of course, we know. 0, 90 degrees, 180, 270, and then all those that are coterminal. The special angles, of course, were 30 degrees, 45 degrees, and 60 degrees for those who use a special triangle. So we're going to try to do that in this session. Plus, we're going to look at the unit circle, also known as the trig wheel, and how we could use that to calculate values. Well, we may not do too much with that today, but we will do more with that later. We're going to use the TI graphing calculator to find trig values of any angle, so please make sure you have this handy. Find the inverse of a trig function. People get really confused about this. There is a big difference between finding the inverse of a trig function and the reciprocal function. Remember, we've talked about the reciprocal partners? That's actually a multiplicative inverse. We're going to be talking about a trigonometric inverse. Very important. But as you use it, it will be clearer and clearer. Let's start with unit circle. When we control the radius as being 1 for this circle, it has wonderful implications for us. We know that sine is the vertical over the radius, y over r. So if r is 1, then we really simplify it a lot, don't we? We can say that sine of the angle is simply y, and cosine of the angle is x. And then we can say any point on the circle could be written as, instead of xy, could be written as cosine theta, sine theta. Does that seem right? Let me, I think I sized this correctly. So, you could have a point on the circle, P, and it represents, as far as a trig function goes, x is your cosine, and y is your sine. Keep that in mind, because when we use the trig circle with a radius of 1, we can determine quite a bit just by looking at what these point coordinates are. Setting the mode that you want. Well, we need to determine whether we want radian or degree. We're going to start out here talking about degree. The other thing you want to look at is float. Let's pull over the calculator and we'll play around with it for a minute. See if I can find it myself. Turn it on. We're going to go to mode. And you see we've got normal, scientific, and engineering. Typically will be normal. And then float, we can choose the, oh, how do I do this? Whoops. I want to delete that. Clear. Okay. Try it again. Mode. And I'll go down and over to 4. And now, if I go to, let's say, sine, oops, did I check degrees? Let's see. Oh, I was in radians, so let me go down here and set this to degrees. Enter. And now I'll do a trig function, sine, oops, no, not twice, sine of, let's see, how about 60 degrees? You see what happened here? I got my answer because I have it in float 4 significant figures from that decimal point. Okay? So you might want to do that. Certainly when you're giving your answers for any trig value where you can't give it exactly, where you have to do an approximation, please give me 4 decimal places. The cosine of 40 degrees, let's do that one. Cosine 40 degrees, 0.7660. The sine of 40 degrees, I actually don't have to close off that parentheses, 0.6420. Remember what we discovered about cofunctions? Well, the sine, if I take the complementary angle and I say the cosine, what's complementary of 40? It's 50, right? If I take the complementary angle of cosine, I get exactly the same as the sine of 40 degrees. Just thought I'd put that in there for now. Prove these values are correct by plugging them into the Pythagorean theorem. Oh, okay. All right, we'll do that. So that would mean I'm going to be talking about the cosine of 40 degrees, which is cosine, we'll do it all over again, of 40 degrees, and I'm going to square that, right, plus, whoops, not times, sorry, I'm wasting your time, try it again, x squared, which would be the cosine of 40 degrees squared plus, I'm going to use parentheses just because I'm paranoid about not having enough parentheses. I don't know if I need them or not. Sine of 40 degrees squared, and then I'll close that parentheses. According to the Pythagorean theorem, what will this equal? X squared plus y squared should equal r squared. Come on. Enter. Come on. Oh, why is it not working? There it is. Guess I wasn't touching it hard enough. So that's a little proof. Now let's look at your calculator for a minute. Here, let me pull it over again. You notice on your calculator the sine, cosine, and tangent keys, sine, cosine, and tangent, they have sine, and it's got a little -1 as sort of an exponent, it looks like. That's actually the inverse function of sine, often referred to as arc sine. Then we've got arc cosine and arc tangent. That's an inverse function. We're going to learn about that shortly. And the way you get to it, notice how they're in yellow? You'll go to this second key, and then when I hit sine, I actually get inverse sine. We'll get back to that. find the following. I don't think I'm going to take the time to do all of these. You can finish them up in class. Let's start with the sine of 29 degrees. Let me just clear this. We know we're in degree mode, nothing has changed. Sine of 29. And there it is, 0.4848. Let's skip over to this one. It's the only one I have in this practice set from Schwartz, which is anything other than degrees. What do I need to be in order to do that? I don't want to be in degree mode, do I, for that one? I want to be in radian mode. Let me put it in there. Okay. So now I can do tangent. Tangent. I'll put in 7 and then pi. I've got an exact value for pi there. Divided by 8. Oh. And it turns out to be negative. What do you think of that? Well, if you were, and I probably should have recommended this to you, when you do these, it might be a good idea to draw the angle. This would be 4 pi over 8. This would be 8 pi over 8. This angle we're talking about here is about like that, which puts it into the second quadrant. Which two are positive in the second quadrant? Not tangent, right? So we expect that tangent in that quadrant is going to be negative, and it is. So you go ahead and do the rest of these in class, or if you have some time with your homework, you can do them at home. Okay, we're going to work on, let me choose B. We're going to work B. So, cosine of, let me make sure we're in degrees. We aren't. We need to be in degrees. Okay, so clear. Cosine, we're in degrees now, so 1, 2, 6, second, apps, and I have the sign I need there for degrees, and 42 minutes, which is also found in angle. Just go down to minutes, and 53. Now, seconds isn't found in this function, so the way I'm going to do that is with my alpha key. Alpha, and right over here on the plus side, and there's my answer for that. It turns out to be negative, and if we think about that, that makes all kinds of sense, doesn't it? Because 126 degrees is going to be over here. The only thing that's positive over here are sine and its reciprocal partner, so we do expect this answer to be negative. So we just did a very few of those examples. You can do the rest of them later. Evaluating trig functions using a calculator. You could find all 6 trig functions for a 37-degree angle. You can approximate to 4 decimal places. You can use float at 4 to help you with that. Now, we don't have any trouble with sine, cosine, and tangent. But what happens when I want to do the reciprocal functions? We don't have any reciprocal key. So, for example, if I want to find cosecant of 37 degrees, what do I know about it? It is the reciprocal of the sine of 37 degrees. So what I can do is, let me make sure I'm still in the right mode. I am. I can find the sine of 37 degrees. That's not what I want, really. What I want is the reciprocal of this. How do I, here's the reciprocal key. I can use that. And now I know that the cosecant of 37 degrees is this. The other thing, I could do it all in one step. I could say 1 over, so we'll use divide, the sine of 37 degrees, and I get exactly the same answer. So you can either find the sine first and then take the reciprocal, or you can do it all in one step, whichever way you like best. So you're going to do that to find cosecant, secant, and cotangent. You find its reciprocal partner first, then take the reciprocal. This is the reciprocal key. There is a lot of confusion with the reciprocal key and the inverse functions. We looked at this a little earlier. Sine with a -1 does not mean reciprocal. It means inverse. Reciprocal is the multiplicative opposite. And just for example, let's look down here. With 3x equals 9, we can multiply by the reciprocal of 3, which is 1/3, to undo the operation. So it is the inverse of multiplication. Sometimes we think of it, instead of being the multiplicative inverse, we think of it as dividing. So multiplicative opposite, maybe that'll help us use that word. That's when we're talking about the reciprocal partners. Inverse is something we're going to do right now. First, we're just going to deal with the concept, and then we'll apply it to trig. You will remember this from algebra. If we interchange x and y in the equation of a relation, it produces an equation of the inverse. So what is the inverse equation for this? Well, every place we have a y, we put in an x. Every place we have an x, we put in a y. And if I were now to solve for y, I'd have 3y plus 2. I'm just going to swap sides because and subtract 2 from both sides, so I get 3y equals x minus 2. And then I'm going to divide both sides by 3, so I end up with y equals x minus 2 divided by 3. That's the inverse of y equals 3x plus 2. Find the inverse of f of x equals x squared. Remember that this is just a fancy way of saying y. Y equals x squared. Use it. That's the function notation. So the inverse, I'm going to have these swap roles, and I'll have x equals y squared, right? Every place I have a y becomes an x. Every place I have an x becomes a y. Now if I'm solving for y, which I would have to do in order to use this notation, this is the inverse of function f, I would have y equals plus or minus the square root of x, wouldn't I? Plus or minus the square root of x. And actually, that couldn't qualify as an inverse function. Why not? Well, if we graphed it, it looks like this, and it wouldn't pass the vertical line test. So I guess I would have to choose one or the other. So I would choose the plus and just write it like that. Find the inverse of function f of x when function f of x is 5x plus 15. Okay, so again, that's just a fancy way of saying y. And if I rewrite this with, this is a y, 5y plus 15, 5y plus 15 equals, now instead of saying equals y, I'm going to say equals x. We interchange them. I'm going to have 5y equals x minus 15. Y equals, I'm going to divide everything through by 5, x over 5 minus 15 over 5, but that would also be known as 3. So I think right here I would write 1/5 x minus 3 is the inverse of function f. What change would you expect from the graph of an equation, going from the graph of an equation to the graph of its inverse? Well, remember we have exchanged the independent and dependent variables, haven't we? So an interesting thing happens with the graphs. Here's the one we just worked out. Let me show you what it looks like. I prepared this in advance. Here is, oh, why don't I do the original one first. This is what we started with. Right? Does that look right? It has a y-intercept of 15. These are 5 by 5 grids. And it's got a slope of up 5 over 1. So over 1, up 5. That works. For the inverse function, it's got a slope of 1/5, so a very shallow but still positive slope, and it's got a y-intercept that is negative. So there it is. The thing I want to point out to you is that if we look at the diagonal, and if you picture folding this whole thing on the diagonal, what would happen? This function will lie right on top of this portion. The inverse will lie right on top of the original function, and the same will happen on this section of the graph. So this is actually a mirror image of this if you look across the diagonal. That is always true for inverse functions. Now, looking at this one, which we're very familiar with, this is the parent graph of a quadratic function. Parent, of course, being the very simplest quadratic you could have. I think I drew that rather poorly. And now the inverse, the positive piece of it, and the inverse, the negative piece of it. We recognized we had two, a positive and a negative. And you'll notice again the diagonal marks a mirror image. If you folded this along the diagonal, these two would lie right on top of each other. if the math doesn't make that much sense, let's go to just a common sense thing. Let's say I drive from the Portsmouth traffic circle to the Portsmouth Regional Hospital. We're mostly familiar with this, aren't we? We'd be heading south on the Spalding. I live in Rochester, so I'm already heading south. I'm heading south on the Spalding. I enter the Portsmouth traffic circle. I travel only halfway around it, right? So I come down and travel not even quite halfway around it, do I? And then I head south on the Route 1 bypass. And when I get to the sign that says hospital, which is at Borthwick Avenue, I take a right and travel down that little ways, and then I go into the hospital parking lot. So what would the inverse function to my function, which I defined up here? I called this the drive car function. So what would the inverse be? Well, the inverse would have me starting at the hospital, wouldn't it? Starting at the hospital. Then I'm going to take I'm so bad with right and left. Then I'm going to take a left onto Borthwick and a left onto the Route 1 bypass. And, well, actually, I can't exactly do that in inverse, can I? Because I can't go, but I could go right back like this. I think this is so much fun. I actually got from Google Earth, I got a picture of this. So the original function, I mean, can't we define almost anything as a function? The original function was I'm coming down the Spalding. I go around the traffic circle onto Route 1 bypass. I take a right. Whoops, not there. Go a little further. Ooh, I wouldn't be getting to the hospital too easily there. Take a right on Borthwick and then go into their parking lot. The inverse of this would undo, that's the point. The inverse will undo what you already did. So if I want to end back at the traffic circle, I'm going to, now instead of taking a right, I'm taking a left. Instead of taking a right, I'm taking a left, and then I'm back at the traffic circle. So, the inverse of any function works in reverse, undoing each step along the way. Work in reverse and do the opposite. So if I took a right, now when I do the inverse, I take a left, just the opposite. And you'll notice I started at the end and worked back towards the beginning of my function. You're going to do the same thing mathematically. How about this one? We have a function, which is that you take your input, x, and you divide it by 3. So what would the inverse be? Function f divides the input x by 3. So the inverse is going to be, we don't have to worry about reverse order because there's only one thing happening here, dividing by 3. We're going to do the opposite of dividing by 3, which is multiply x by 3. So symbolically, it looks like this. There's our input, we multiply it by 3. If we did it numerically, x is, when x, let's take this one, when x is 9, and we divide it by 3, we get y, which is negative 3. So now I have swapped my x and y. When my x is negative 3, I multiply it by 3, I get 9. Graphically, what does my inverse function look like? It's just a straight line that looks like this. How about this one? There's more than one thing happening here, isn't there? We've got an input and we're subtracting 2 from it, and then we cube it. Function f subtracts 2 from x. Function f subtracts 2 from x and then cubes the result. The inverse is going to go in reverse order. So what was the last thing we did? We cubed. So in reverse order, the first thing we do is take the opposite of cubing. What's the opposite of cubing? Take the cube root. What was the first thing we did? We subtract 2. What's the opposite of subtracting 2? Adding 2. So the inverse function, just logically, has to be the cube root of x plus 2. When we look at a table of values for the inverse, one way we can look at it is before we were working with the inverse, we had a -1, that was back here. A -1, we subtracted 2, that gave us -3. We cube -3, we get -27. Once we do the inverse, the x and y changed. Now we have -27. We take the cube root of that. It gives us -3 plus 2, a -1. Graphically, it looks like that. Finally, as I promised, we're going to look at the inverse trig relations. Now, what's the inverse all about here? We're going to start right here with something we're familiar with. When we are given an angle, like the sine of 30 degrees, we can figure out what the ratio is. Cosine, we can figure out what the ratio is. We are given an angle, we find the ratio. Well, in inverse, of course, it's going to be just the opposite. We are given a ratio, and we have to find the angle. So the input that you put in to arcsine is always going to be the ratio. Now, your answer is going to come out in accordance with whatever mode you have chosen your calculator to be in. So there is a possibility of getting 2 different answers. If you're in radian mode, your x is going to come out as the angle measure in radians. If you're in degree mode, your angle measure will come out in degrees. Okay, x is the angle measure. If we have the sine ratio 0.7523, what is the first quadrant angle that has that sine ratio? Now, we'll talk more about which quadrant. It becomes very important. Right now we're going to assume everything's in the first quadrant. So we have a ratio and we want to know the angle. So we don't need to use sine, we need to use arcsine, just the inverse. Oh, wait a second, I should have checked mode. What mode am I in? I'm in degree, okay. So my answer is going to come back in degrees, 0.7523. Okay, and what is the angle going to be? Well, 48 let's say 8. My answer is in decimal degrees. What if I want to change it to DMS? What could I do? I could go to second function, angle, and go down to number 4. Hit enter. And it says it's 48 degrees, 47 minutes, and if I round this, 24 seconds. All right, let's see what I got when I figured this out last summer. I'm hoping this is going to look familiar. Wouldn't that be embarrassing if it doesn't? Oh, thank goodness it does. I wouldn't then know whether I made the mistake in the summer or I'm making the mistake now. That looks very good. You're going to do these. We're going to save this and have you do these in class. I'll be there to give you some support if you need it. What if you need to find the inverse trig function? Obviously, we don't have any key for arc cosecant, arc secant, or arc tan. So we're going to work the reverse of how you found these. Remember, when you were looking for, oh, let's go back there. We'll get there eventually. This one, yes. When you're looking for cosecant, you found sine and then took its reciprocal. So now what would we do? We'd find the reciprocal first, wouldn't we? Because you always work in reverse. Do the last thing first. See if I can get us back there. Okay, so take the reciprocal of the ratio 2.4. Let's do it together here. So we know that we're talking about a ratio. We want to find it's the cosecant is 2.4. So if the cosecant is 2.4, turn it on, 2.4, then its reciprocal partner is sine, which would be 0.4167. Okay. Take the arcsine of that, and we'll know what the angle is. Point 4166. I'll put a lot of sixes in. 7. You don't have to do that many. And we get just what we're supposed to get. But we could do it all in one step by finding the sine of 1 over 2.4. And here's some more for us to do in class. Also in class, we'll have homework number 1. Boy, we are going to be busy in class. I will see you there. Thank you very much for your kind attention. I do appreciate it.